So our final talk of the morning is Andrei Linde, who's going to be talking about cosmological attractors.
Oops. Okay, being, well, the second talk of the Russian part, I should say that I will not follow the lead of our own revolutionaries who first were speaking the same thing and then they just finished killing each other. No, I partially agree with some of the things which the previous speaker said. Okay? So now, okay, now let me go further. This is just, well, let's remember Stephen. Here he is. And that's Andrei Sakharov. So two of my heroes, to whom I may also, well, address this in the same way. They're my attractors and heroes, not always for the reason that they were always saying absolute truth, but for the reason that they were very bold, very knowledgeable, and what they did, they have led to, well, real revolution in some aspects of our understanding of the universe. In particular, Sakharov was one of the first who in '84 suggested the possibility that if our space is created from compactification of multidimensional space, because of the combinatorial, well, magnitude of different, how you combine it, you will have exponentially large number of different values of the cosmological constant, which he suggested in '84 would solve the cosmological constant using entropic principle. And this is, of course, the basis of the multiverse, which some of us hate, and some of us, like me, really love. Okay, so let's go forward. This is what happened later for me. This was the beginning of my, well, encounter with Steve Hawking. In fact, the beginning of encounter, I don't remember whether I told it at the previous conference. The beginning of encounter was pretty dramatic. I was giving my first talk on new inflation, and after that I was translating his talk on inflation. And in his talk he explained how the Goose model didn't work, and then and I was translating, and then he said that there was an interesting suggestion how to solve the problem by Andrei Linde, and happily translated. And then he said, but this solution is completely wrong. And for half an hour I was translating why the theory is completely wrong in front of people who were in the future going to give or not to give me any position. Okay, so I've never been in a more stupid situation in my life. And after that, I said that I translated, but I disagree. And Steve, would you like me to tell about it, to talk about it with you? And he said, yeah. And then he rolled in some place, and he was lost for 2 hours. So the whole institute was in panic that famous British scientists were lost in Russia. And meanwhile, I was talking to him, and he said, yeah. And his student would translate, but you did not say that before. And they continue, they say, you did not say that before. And after that, he invited me to his hotel. And after that, he started showing me photographs of his family, and we became friends. So that's how it was. It was pretty explosive. And this was a conference which she started here after that. And it was by far the most, well, fantastic conference of my life, where, well, many different things have been really done and really achieved. I may, well, one part of summarizing it is to say this is what Alan Guth said in the beginning of the conference. Well, before that, it said that there is no such thing as free lunch, but the universe, he have in mind, of course, inflation in the universe, is an ultimate free lunch because you get everything from nothing. And then leaving this conference, I was pretty impressed by free lunches which were offered to participants in Cambridge. And I said, now we know that the universe is not just a free lunch, it's an eternal feast where all possible types of dishes are served. And that was after I realized that when you have even new inflation in the universe, it may be divided into different parts with different regions with possibly different dimensionalities. And I was absolutely thrilled by this possibility. So those who doesn't like like multiverse, that's okay. This is the history of evolution of inflationary universe, how I recognize it. The first, it was modeled by Alexei Starobinsky, and it was well, modeled based on quantum corrections to gravity. Later, he modified it and made it r plus r squared. His formulation actually was different from inflationary theory. Instead of solving uniformity problem, he assumed that the universe is absolutely uniform. On the other hand, its experimental predictions are just fantastic. Then there was Alan Guth, who suggested very clear motivation for inflation, and this was the reason why I value what he did, because he suggested, he actually explained why it is necessary to have something like that. But as he himself admitted, it did not quite work. So then he have written a paper together with Eric Weinberg for almost 100 pages saying that it cannot be improved. But because of the bad connection in mail between Russia and US, I received his paper only after I already improved it. This was new inflation, and this new inflation had approximately 1 year of lifetime, because after the conference at Nuffield workshop, we have learned that the fluctuations produced during inflation there are way too big. In fact, I've learned it 2 months before the Nuffield symposium at some conference in Tartu, where Starobinsky gave a talk with the same content. And then I kind of improved it, and this is chaotic inflation model, and more or less the family of models which we study, it's based on the models of that type, because they do not require hot Big Bang, they do not require the huge universe with, well, how you can balance different densities in different parts and how you go. It's sufficient to start with a Planckian size domain, and if you have sufficient order there, that's enough for the universe to start with. And it inflates, and for a long, long time, this theory was a prototype model which we study right now. However, things with predictions, this model will kind of died a few years ago by combined well, effort of WMAP and Planck. So let's see this list of predictions. I am not going to list all of them, but it's kind of interesting for me when I see, well, in the popular press, that inflation does not predict anything, because, well, okay, anyway, and there are many, many different things. Many of them were near-death experience for us, for inflationary theory. In particular, the universe is flat, and in the 90s we were told that, no, we know that omega is equal to 0.3, and we tried to suggest models which explained how omega can be different from 0.3. I participated in that. And for a while it was fun, but then gradually you notice that how all of these models are just dying and dying and dying. And the only model which remained from this time is a really ugly model, and I say it with authority because I invented this model. So I know how difficult it was to do it, and then suddenly we were saved. We were saved when this dark energy gave extra 70% contribution. And so many other things. For me, another thing was equally, you see this is 9 points, so just skipping all of them, coming here. For me, this was absolutely crucial, because in 2012 and coming to that, there were, well, persistent rumors that, especially since the WMAP was giving very, very broad range, somewhere centered at about 20, so FNL local should be much larger than 1, which would kill 90% of inflation more than 99 or 99.9, depending on what you measure it. I would say the simplest, best, well, whatever models would be killed. And then all our students and all our postdocs were involved in calculating and in suggesting inflationary models which would lead to non-Gaussianity. Models were ugly. People were happy, because for all of these postdocs, this was a guaranteed future. Because, you know, it's like when Anna Karenina of Tolstoy, all happy families are similar to each other, all unhappy families, they're different. So you can produce lots of different inflationary models, and your employment is guaranteed. So when finally Planck found non-Gaussianity, they asked me, "Oh, you're probably so upset." And I say, "No, I'm so ecstatic." So because this was just, well, all of the best inflationary models were saved. Now, coming to this Planck data, this m squared phi squared model is outside of this magic blue region, so we needed to do something about that. And it is possible to do something about that. And it is not horrible, it is just, it's possible. It's if you take m squared phi squared and just take another two polynomials, then you have three parameters, m, a, and b. You have three observables, amplitude of perturbations ns and r, and these three observables can easily tuned by finding the potential looking like that, which fit to all presently available inflation-related data. So you would not even consider it any problem at all, especially from the point of initial conditions. You can start here with Planckian density. So yeah, but now, nevertheless, the best models which explained data and just well happen to show point to the same region, it was Tarabinsky model. Okay, then there was a model which I myself forgot about it. We, with my student, have proposed Goncharov have proposed a model which has a very similar potential, exponential one, and come to the same point approximately. And then there was Higgs inflation, all coming to the same point. And for a while we were looking and looking at it, and only the Planck 2013, when they said that non-Gaussianity and this point is certain, forced us, Renata and me, to consider seriously this possibility to try to understand what is going on, why all of these inflationary models point to exactly the same point. And one could do it from general considerations like, well, what is pressure and what is energy, but it would not be enough for us. So we tried to study it, and we found a very large class of models which actually predict, depending on some parameter. But if this parameter alpha is of the order of 1, which is most natural, then it all points to exactly this point. So now what is this class of models? What is their meaning? And after all of this work, because it was done in superconformal theory, in conformal theory, in, well, extended gravity, and many, many different things, there is one thing which crystallized. And let me show you the simple version of it. So let's start with my model. This is chaotic inflation, simple version, m squared phi squared. The only thing that I need to do, I need to add here, modify kinetic term here. So the modification is such that at small phi, it's the same kinetic term as here. At large phi, there is a boundary where you have a singularity in kinetic term. Okay? So it's not that we wanted particularly to invent this singularity there, but we found that that's exactly what happens when you have, well, Higgs inflation, and you interpret it coming from Jordan frame to, well, to Einstein frame. It's the same thing which happens when you have a Stravinsky model, r plus r squared, and reform it, represented in terms of scalar field. And then we found a similar mechanism when you start well, constructing inflationary models starting from superconformal theory. And we found that this mechanism is rather generic, and then this form emerged, especially after the collaboration with Roest. So what happens is this. This looks very, very dangerous. This looks like you have a singularity in kinetic term. But then these are not canonical variables. So you can always solve equation representing this field phi in terms of canonical variables, and then suddenly this term becomes normal canonical term, but this one, instead of m squared phi squared, becomes m squared tanh of phi. And tanh has a limit, 1. So when you have phi squared, then it just becomes like that. So this is what happens. An interpretation for a complex field can be obtained as follows. This again, this is later interpretation, but this interpretation was also quite telling for us. So if you study complex field, for example, and look at the kinetic term, terms like that all the way are well studied by people who study supergravity and string theory, and it is called Poincaré disk, and it was well represented by the painting of Escher. And this quantity alpha is even related, as Renata found, to radius of this Escher disk in Planck units. So this is what I did. I just projected this Escher painting on quadratic potential. So what happened? The size of all of these angels and demons, physical size, is the same. But then you see most of them are living here near the boundary. So boundary is too many of them per square centimeter. But then if you go to other variables, the canonical variables, suddenly you see that the size of them is very, very large, and it's just potential bends like that. The height of the potential remains the same, but you have a plateau. Now, another thing, if you start with other potential, why don't we study with V of phi? Usual attitude of many people who study stories like that, V of phi, oh, well, you have m squared phi squared, but then I add lambda phi to the fourth, but then I add phi to the sixth, phi to the whatever, and then how do I know that I can even, have any idea with what happens with the potential? So let's right now start with whatever arbitrary potential, and then make this change only in the kinetic term. And then suddenly it becomes potential as a function of time. And asymptotically, this is function of 1, so potential becomes constant. Therefore, you have plateau potential. That's exactly what we want to satisfy Planck data. And now, to understand physically what does it mean, this is what I just will push the button and generate at mathematics, generate you a random potential by adding many sinusoidal waves. You look at it and you say, no inflation in this potential is too sharp, no way to get inflation there. And then you make this transformation after you use this Poincare disk. You make this transformation, the central part does not change because the only modification is at the boundary of the moduli space, okay? But at the boundary, the only thing that you need to know is this part, and this part is stretched, and this part is stretched. So if you are here, then you are rolling in ADS space, actually not for long, because your space is going to collapse soon. If you are here, then you are rolling in de Sitter type of space, and then you are rolling here, and then you have inflation. And what is interesting, this is pretty generic. So the idea I formulated like that: inflation in the landscape, inflation, just normal inflation, is helped by inflation of the landscape. I'm inflating this part, and I create the potential, which is very good for representing inflationary theory. Then we formulated it another way, because the fact that you have a singularity at the boundary, you can make a change of variables, and you can reformulate it like that. This is just a pole singularity, dt over t. So if you have your fundamental variable is logarithmic, and then this is v of t, and you expand potential in terms of canonical term, you always see here some constant. Constant is the value of the potential, the value of the potential at the boundary here, okay? So you have a constant, and then because of stretching, the next term is always exponential, independently of what the shape of it is. And therefore, in the leading approximation in 1 over n, where n is the number of foldings, you have universal prediction for all of these theories, this and that. And we're not only saying that it would be nice to have these kind of predictions, that they, aesthetically more pleasing, but instead, in all of this class, automatically you have this prediction as a property of just the consequence of this kinetic term. And R, it depends on alpha. Now the question is, what is alpha? If you have alpha equal to infinity, then you're back to the previous story. But if alpha is any, normal, and we will discuss it later, then you have a prediction very similar to predictions of Starobinsky and Higgs inflation. So the basic rule for broad class of cosmological attractors, and why we called it cosmological exactly because of that, the attractors. Because you start with very complicated story, and then your predictions do not depend on what kind of stuff was there, but they depend only on the height of the potential. So here it is, okay? So the spectral index depends only on the order of the pole in the kinetic term, and the tensor to scalar ratio is a residue. So if you know kinetic term, then this is a prediction. Usually, inflationary testing was concentrated on checking potentials. And then what will happen if I add to this minimal theory something else, just old stuff, okay? I can add here another theory of this type, or let's just do something simple. It really does not matter for what I'm going to say. So let's we'll put here normal theory, a normal potential, normal kinetic term. The total potential of these two theories will be a combination of this one, which is perfect touch, giving you perfect agreement with, well, perfect, with whatever we know right now from Planck. We still need to be careful about saying perfect agreement, because predictions do depend on tiny details, and tiny details may be important because right now we have, well, the accuracy of experiments are growing, and tiny details, for example, the reheating in the theories. So, for example, in Starobinsky model, typical reheating is very inefficient. In Higgs inflation, typically reheating is super efficient. As a result, the number n for these theories, this capital N, for one of them and for another, they will be usually different by about 3. And this is not a very important thing, but it becomes important when your accuracy of determination of NS becomes increasingly better. So now we look at this and then we say, okay, so here I have my singularity. What can I say about interaction, the strength of interaction of this field after I made it canonical? What is the interaction of this field with any other fields I have in the theory? Well, so what is this thing? So you usually have your potential. You take second, third, quartic, whatever, derivative of this potential with respect to different fields, and you get vortices, which describe your strengths of interactions, and you are describing it in terms of canonically normalized field. So in order to get it, like for example, I want to have interaction of canonical inflaton with two other fields here. I take third derivative, but this is with respect to canonical. But potential is expressed in terms of previous ones. So if I have phi squared, sigma squared in this variable, I will take easily derivative in this variable, but I must also multiply by derivative of old phi with respect to the new phi, and gives you exponential suppression. As a result, when you have phi very, very large, your all coupling constants of the inflaton field with anything else will be exponentially suppressed. So this is, well, asymptotic freedom, much greater freedom than in any other theory. This is what I usually would generate if I decide to generate random potential. Random potential, looking at these two-dimensional, two different fields, and you say, no inflation is possible, everything is too steep. And then I represent it in terms of canonical variables. And I see here lots of valleys, and they are falling to different values of minima with different values of cosmological constant in each of them. So you may say on philosophical grounds, no, I don't want to have multiplicity. And I say on practical grounds, yeah, I want to have a lot of different types of coffee in my shop. So I do not say that this is bad. I say that this is wonderful. If you have double attractors, if you have two attractors with two different values of this parameter, one alpha, another beta, then I have effective potential, which is function of two of them. And depending on whether I'm rolling here in this direction or I'm rolling here in that direction, I have two different predictions for R. I have the same prediction for NS, but I have two different predictions of R. And then how many such fields do I have? Well, I don't know. So far I discussed it, and mostly I will concentrate on that. So far I discussed theories which, well, just theory of scalar field, not going to supergravity, etc. But that is what we are doing right now. We are trying to go in supergravity, in string theory, trying to find out reasonable realization of the theory. For a long time we had problems. We have these models, and then we have this minimum, and this minimum in most of the simplest models, it's always Minkowski. Well, not always, but the simplest, the nicest, etc., Minkowski. And supersymmetry breaking there is absent. It was easier to find such models. Then we start trying to modify them to make it de Sitter or anti-de Sitter and in additional supersymmetry. And there was a progress very recently, literally about a month ago, when we found a very economical representation of what can be done. Renata will mention it. I will show you equation. It looks, well, horrible because it is actually this is a function which was used by those people who introduced supergravity quite a lot. And it has in it information about Keller potential and superpotential just frozen in it. So what is found that the theories of some specific type using what is very important, some special scalar field which has interesting interpretation in string theory called nilpotent field, then you can write this. You want any potential, you write this potential here. You want any shape of the potential, you want to reproduce it in supergravity. And you write here this potential, push the button in your Mathematica, it calculates your potential, and it produces you exactly what you plugged in accordance with all rules of supergravity calculation. So in general, if you want a given potential, we know how to do it, and on top of that, this W0 gives you supersymmetry breaking, gravitino mass in the minimum, and this will be this W0, this lambda, okay? Lambda is an independent parameter which is related to W0 and, well, actually I saved the time, I did not write here this F S squared. So anyway, I can have here cosmological constant, and I can have here gravitino mass. And this compared to everything that we were doing before, it's pretty economical. Now, this model, this particular model, shown here, that because we start playing, what if we have two different cosmological attractors in supergravity and strongly interacting? Because I said, well, there is no interaction asymptotically, but let me try to go to the limit and let me consider two attractors strongly interacting. In particular, this model says that you have two attractors corresponding to alpha equal 1/3, and there is some deep reason why alpha 1/3 is special. Maybe Renata will mention this. So suppose you have, and I want these attractors to kind of forcefully coincide so that two inflaton fields are equal to each other. One can do it using this construction because this, well, term forces field phi1 and field phi2, where phi is related to a real part of the original variables. So I want them to coincide. And then we get inflationary potential, which looks like that. So that's how it is. You have two different attractors with alpha equal 1/3, and then they merge, and they produce attractor with alpha 2/3. And this was the center of the construction which Renata Kalush recently introduced, where you have several disks existing in this maximal supergravity, and they can merge, and as a result of the merger or absence of these, you can have predictions corresponding to alpha equal 1/3, 2/3, etc. Maximal is 7/3. And they are different in terms of gravity. The prediction for R goes from 10 to the minus 3 up to 10 to the minus 2. And depending on those experimentalists with whom you talk, some of them say, oh, I love this, 10 to the minus 3. Others say, oh, I love it, 10 to the minus 2. But for all of them, it gives them targets, and targets which may have some relation to string theory. But here, when we were plotting this potential, we plotted only the minimum here, what happens at the end of inflation, because this is how inflation ends. And then if you want to know how inflation starts, we need to plot the full potential, not cutting the upper part of it. And what we find there, that you have lots of inflationary plateaus, de Sitter plateaus, each of them will work as the beginning of inflation. So you end inflation when you roll to this final minimum, but you begin inflation at one of these plateaus. We did not expect that structures like that will universally appear and appear in different models we have. So now I'm returning to the problem of initial conditions, and I have just 5 minutes to explain how the universe was born and why it is natural. And actually, it appeared to be so simple that I can manage, I think, to put it in 5 minutes. So the story is that this new set of potentials, they are, well, the simplest one-field model, they are asymptotically flat, so they are not very much different from cosmological constant. They are almost cosmological constant almost everywhere except for this tiny vicinity. So now the question will be opposite, not how do you start inflation, but can you avoid our universe entering de Sitter stage if there is a cosmological constant there. So you have matter, and this matter, in principle, it can, well, collide, collapse to the black holes but unless the whole universe collapses, then whatever remains after the universe expands, the normal matter density of it gradually decreases, cosmological constant remains, and then you just fall down to this plateau and you have no other choice rather than to inflate. So it is right now formulated like that. Only instant global collapse within 10 to the minus 28 seconds can save inflationary model in in this scenario from inflation to begin, okay? And the universe collapsing at 10 to the minus 28 seconds, you can safely say that it is unborn universe, because certainly there are no cosmologists asking any questions why the universe is flat, whatever. But that's, of course, anthropic. Yeah. Anyway, so that was especially, well, confirmed by calculation by these people, and especially Will East. And sometimes, okay, anyway, so Will East, he worked with Pretorius, and he used his method by Pretorius, studied for black holes to see whether it leads to something really bad in an inflationary universe. So we start with totally non-uniform universe, grossly non-uniform, okay, of the order of 1. And cosmological constant well below. And then, oops, okay. And then calculations run, and what you find eventually, that there is one region of the universe where you, for a black hole, but then see black hole start shrinking. And it's not because black hole can shrink, black hole cannot, but it is shown in the graph where the whole universe continues expanding fast. So all of these results obtained by these calculations can be formulated in a very simple way. So it is known that dropping money from a helicopter may lead to inflation unless all money miss the target, like fall to the, well, right, okay, to the ocean. But then this is what happened, and this analogy actually was suggested to me by Starobinsky, who read this article in Scientific American saying that initial conditions for inflation, well, are unreasonable. I mean, this is, okay, I say nothing. Okay, saving my time for 2 minutes. So what I say is that if you have money dropped from helicopter and you have infinite plateau, then most cases they land in a proper place for inflation to start. And if you have this model, which I already shown to you, then there is another possibility, because in this cross-section, this field has a potential which is still quadratic. So you can start inflation as in the original quadratic potential model, but then you have all predictions perfectly given by the second model. So no problem with initial conditions, no problem with Planck. And then returning to this cascade inflation, I have 3 slides for 2 minutes. So this is my original one, this is the full one, and that's how inflation actually happens. So it goes here and then eventually goes here. This is something which we call cascade inflation. So here I am with my conclusions. Cosmological attractors allow us to reconsider many usual assumptions. We just did not know that this is possible. But Planck data forced us to rethink what we like, what we don't like, and maybe there is some reason why several different models have similar predictions. And when the reason was identified, we start thinking and exploring these different models. And what is interesting first, that many problems which previously were very difficult problem of large field inflation, right now looks like if you make one single change for one single field, not for all of them, but just for one of them, and you assume that you have this specific term, then many of these problems simply disappear. And then from the point of view of model buildings, there are some models which give you interesting predictions for R, and they are in a very interesting range cosmologically. I finished. Thank you.
So thank you. Questions? And I remind questioners to grab the microphone.
The original Starobinsky model was not R plus R squared. It was one based on
Yes, indeed.
phenomenon. Can you explain why and when there was the transition?
Okay, that's an interesting story. Well, first it was based on the conformal anomaly, and as I understand now, the conformal anomaly was not even written there completely, because we now know that some other terms should be added. And then he himself have seen that it is better to modify the theory to bring it to normal way, because in order to describe all data that we see right now, Slava will correct me, but I believe that you would need about 10 to the 10 different fields. So he just decided to have this term R squared separately and edit it. But it was not even obvious to anybody that this term is edited. It was done in some of his models without explicitly writing it. It was explicitly done first, I think, in our paper with Starobinsky and Kaufman in '85. In '84, the model of R plus R squared was studied by Witt, who formulated the theory of a scalar field, but he did not know that it is Starobinsky model. And then Barrow and others studied these models and identified one to another. So it was complicated effort in this direction.
But the coefficient of R squared is fine-tuned, yeah?
R plus R squared, yes, it is fine-tuned. Just any other model which require the parameter, which should be small, and the parameter is small, to describe another small parameter, which is small delta rho over rho. So whether it is fine-tuning or tuning or everything, it depends on the model. Like how fine-tuned is the electron mass, which is 10 to the minus what in Planckian units? Yes, we need it to live, right? Anthropic principle.
So you went from a model that was wrong to one that was not even wrong.
What do you say?
We went from a model that was wrong to one that was not even wrong.
No, we wanted to understand why certain class of models are so successful without any obvious reason giving you the same answer there. But of course, from the thermodynamical point of view, which were described by Slava, you could guess that something like that is possible. And nevertheless, it was, you can guess this and you can guess that. After the final result, you can say this guess was better. What we see right now, there are some physical reasons for existence of large class of models which give this prediction under some conclusion of their internal structure.
Question from Gary?
I was puzzled by your disk model, because there you have two fields and your transformation will only work for the radial fields. So what do you do for the transverse fields or the angular fields?
Okay, you can formulate the theory in a way which have, for example, Kähler potential which satisfy all symmetries, or you can formulate the theory where Kähler potential is have chosen in such a way to emphasize only one of them, which is shift symmetry. And this modification of Kähler potential in the context of supergravity was done pretty recently. I think that probably Renata Kalish will spend some time explaining what is happening there, and the explanation goes in the language of tessellations in Escher paintings.
So you exclude an SO2 symmetry in your example?
Oh, well, you need eventually, usually you just break the symmetry one way or another. Sometimes you break the symmetry by choice of Kähler potential. Sometimes you break the symmetry by choice of superpotential in supergravity, we found that it's way better thing, better method is to have Keller potential, geometrical thing, having flat direction and proper direction, and let superpotential do the dirty job.
Okay, thank you.
All the things you said,
Just a
Andrei,
minute.
all the things you said about the flat potentials and the tangents and so forth flowed from making the assumption of the 1 minus phi squared all squared factor in the denominator of the kinetic term. Was there another reason for making that choice?
Okay.
Could it be different?
The only thing that you actually need is to making a kinetic term having a pole of the second degree. Okay, so the poles of the second degree, they quite often appear again in supergravity, but for us it was a rather gradual choice. I can tell you how we first time we found this model based on the concept of spontaneous symmetry, spontaneous breaking of conformal invariants, and it was like, oh, we had this, we start with this, we start with that, and we make one simple assumption, you get de Sitter space. And then you violate one thing, and suddenly you have a attractor like that. And I said, oh. So for us, it was, I cannot say how exactly this happened. It was crystallization of several different facts and theoretical observations.
Perhaps the final question from Fernando.
So usually when you have flat potentials, you have to worry about quantum corrections. So how would you address the issue about tuning the quantum correction, not changing the flatness?
So there are quantum corrections and there are quantum corrections. What I said is that you have a theory which is written to you. Here is on the blackboard, okay? If in the first approximation, if you start with a theory written like that, this is what happens. This is a theorem, they are flat, period, okay? If you say, but on top of that, this is a part of string theory, and in string theory you have alpha prime corrections and whatever else, and these other corrections can change, for example, the power of the singularity in the pole, whatever. So many different things can happen. So that's why what I said is what I said in the context which I used. Either you have normal scalar field theory, already in this context everybody was saying quantum corrections totally destroy your theory. Okay? So what I'm saying is that if you have started the theory with this pole, the poles seem to be the most dangerous place because you have singularity and kinetic term. But you make transformations to canonical variables in which it is better to make calculations, and then suddenly you see that the pole is actually at infinity. And at infinity, you have exponential freedom, exponentially small coupling constant. So what seemed to be dangerous, actually totally innocent. However, if you start adding something else based on independent considerations, changing these are toy models. The question is whether they are teaching us something or not. And I hope that they do.
Okay, so let's thank Andrei and